Hello friends, welcome to our channel. In previous video, we discussed about continuous function in a metric space. In today's video, we will discuss continuous function on closed subsets of a metric space and some results based on continuous functions and closed subsets. Theorem. Let xd and yd star are any two metric spaces and let f x to y be any function then f is continuous function if and only if the inverse image under f of every closed subset of y is a closed subset of capital X. Proof. In this theorem, it is given that x and y are any two metric spaces with metric d and d star respectively, and f is a function from x to y. Then f is continuous function if and only if the inverse image of f of every closed subset of y is closed subset of x. That is, if we have to take any closed subset of y, then its inverse image is also closed in x if f is continuous. Conversely, if f is continuous, then if any subset, closed subset of y, then its inverse image is also closed in x. So let f be a continuous function from x into y. Suppose capital F be any closed subset of capital Y. That is, capital F is contained in Y. We have to prove that F inverse capital F is closed subset of capital X. Since capital F is closed in Y, this implies Y minus capital F, that is F complement, is open in capital Y. We know that if G is open in Y, then F inverse G is also open in capital X if F is continuous function from X into Y. This result we already proved in last videos, that X and Y are any two metric spaces with metric D and D star. F is any function from X to Y. Then G is open in Y, then G inverse is also open in X if and only if F is continuous. So as Y minus F is open, this implies F inverse Y minus F is open in capital X, but F inverse Y minus F is equal to F inverse capital Y minus F inverse capital F, which is equal to capital X minus F inverse capital F. This implies X minus F inverse capital F is open in capital X. This implies F inverse capital F is closed in capital X. Thus, F is closed subset of Y, then F inverse capital F is closed subset of X if F is continuous function from X into Y. Conversely, we assume that the F inverse image of closed subset of capital Y is closed subset in X. We have to prove that F is a continuous function from X to Y. Let subset of capital Y, then Y minus G is equal to G complement is closed subset of capital Y. So by given condition, F inverse G complement is closed subset of capital X, that is F inverse Y minus G is closed subset of capital X. Now F inverse Y minus G is equal to F inverse Y minus F inverse G. This implies F inverse Y minus G is equal to capital X minus F inverse G. This implies capital X minus F inverse G is closed subset of capital X. This implies F inverse G is open subset of capital X. Thus, if G is open in Y, then F inverse G is open in capital X, and F is any function from X to Y, then F must be a continuous function. Hence, F is continuous function from X to Y if and only if the inverse image of a closed subset of Y is closed subset of capital X. Example, let XD be an infinite discrete metric space prove that every function f from metric space XD to any metric space y d star is continuous function. Solution: let x d and y d star are any two metric spaces and f x to y be any function where x d is a discrete metric space therefore dxy is equal to 0 if x is equal to y and 1 if x does not equal to y for every x y belongs to capital X. We know that in discrete metric space every subset is always closed subset. Let capital F contained in Y be any closed subset of Y, then F inverse capital F is a subset of capital X. This implies F inverse capital F is a closed subset of capital X because every subset of capital X is closed. Thus, if F is any closed subset of Y, then F inverse capital F is closed subset of capital X. This implies F is a continuous function from metric space X to Y by using previous theorem that X and Y are any two metric spaces. F is any function from X to Y. Then if F is any closed subset of Y, then F inverse capital F is also closed if and only if F is continuous. Next theorem. Let x d and y d star are any two metric spaces and f is a function from x to y, then f is continuous function if and only if f of a closure is contained in f of a whole closure. For all a is contained in x. Proof. Let x d and y d star are any two metric spaces. Suppose f is a continuous function from x to y and a is any subset of capital X. We have to prove that f of a closure is contained in f of a whole closure. As a is contained in x, this implies f of a is contained in y, that is f of a is subset of y. This implies f of a, its closure is a closed subset of capital Y, because closure of any set is always closed set. This implies f inverse f of a closure is closed subset of capital X, because f is continuous. This implies f inverse f of a closure, its closure is equal to f inverse f of a closure, because B closure is equal to B if B is closed. Put it equation number 1. Now f of a is contained in f of a, its closure. This implies a is contained in f inverse f of a, its closure. This implies a closure is contained in F inverse F of A closure, its all closure, because if A contained in B, then A closure is contained in B closure. This implies A closure is contained in F inverse F of A closure, its closure, which is contained in F inverse F of A closure, because by equation 1, thus A closure is contained in F inverse F of A closure. This implies F of A closure is contained in F of A whole closure. Conversely, suppose F of A closure is contained in F of A whole closure for all A contained in X. We have to prove that F is continuous. Let capital B be any closed subset of capital Y, then B is equal to B closure. This implies F inverse B closure is equal to F inverse B, which is contained in X. According to given condition, F of F inverse B, its closure, is contained in F of F inverse B, its all closure, because for all A contained in X, F of A closure is contained in F of A whole closure. This implies F of F inverse B closure is contained in B closure, because F of F inverse B is equal to B. This implies F inverse B closure is contained in F inverse B closure. This implies F inverse B, its closure, is contained in F inverse B, because B closure is equal to B. This implies F inverse B is closed subset of capital X, because F inverse B, its closure, is closed. Hence, if B is closed subset of Y, then F inverse B is closed subset of X, This implies f is continuous function from x to y. Next theorem. Let f be a continuous function of a metric space xd into another metric space yd star. Then for every subset B in Y, we have F inverse B, its closure is contained in F inverse B closure, and second, F inverse B, its interior contains F inverse B interior. Conversely, if either one of the condition hold, then f is a continuous function. Proof. Let xd and yd star are any two metric spaces and f is a continuous function from x to y. Since B closure is closed subset of Y, this implies F inverse B closure is a closed subset of capital X. This implies F inverse B closure, its closure is equal to F inverse B closure. Also, B is contained in B closure. This implies F inverse B is contained in F inverse B closure. This implies F inverse B closure is contained in F inverse B closure, its closure, which is contained in F inverse B closure. which proves first condition. Again, B interior is any open subset of Y, because interior of the set is always open set. This implies F inverse B interior is open subset of capital X. This implies F inverse B interior, its interior is equal to F inverse B interior, because A interior is equal to A if A is open. Now B interior contained in B, this implies F inverse B interior is contained in F inverse B. This implies F inverse B, its interior, contains F inverse B interior, its interior, because if A contained in B, then A interior is contained in B interior. This implies F inverse B, its interior, contains F inverse B interior, its interior, which is equal to F inverse B interior. This implies F inverse B, its interior, contains F inverse B inverse, which proves second. Conversely, we assume that either one of the given condition holds, we have to prove that F is continuous. Suppose condition first holds, that is, for every B closed subset of Y, F inverse B, its closure is contained in F inverse B closure. Let B is closed in Y. This implies B closure is equal to B. This implies F inverse B, its closure is contained in F inverse B closure is equal to F inverse B, but F inverse B is contained in F inverse B closure, because A is contained in A closure for all A. This implies F inverse B, its closure is equal to F inverse B. Therefore, F inverse B is closed subset of X. Hence, if B is closed in Y, then F inverse B is closed in X. This implies F is continuous function from X to Y. Suppose condition second holds, that is F inverse B, its interior contains F inverse B for all B in Y. Let B is any open subset of Y, then B interior is equal to B. So by given condition, F inverse B, its interior contains F inverse B interior, which is equal to F inverse B, but F inverse B contains F inverse B, its interior. This implies F inverse B, its interior is equal to F inverse B. Thus, F inverse B is open in X. Hence, B is open in Y. Then F inverse B is open in X. This implies F is continuous function from X to Y. It is sufficient for today. In the next video, we will discuss about uniform continuous function in a metric space. So keep in touch, watch our videos and subscribe our channel for more and more videos on these topics. Thanks to all. Have a nice day. Bye bye.